was a time when Earth did not exist. No oceans, no mountains, no sky, no ground beneath your feet. Nothing that you could point to and call a world. Where our planet now hangs in the darkness of space, a blue-green sphere of extraordinary improbability, there was only a vast, swirling cloud of gas and dust. The scattered remnants of a star that had already lived and died long before our sun ever ignited. Silent, cold, formless, a graveyard of stellar debris drifting through the dark. That is where our story begins. Not with humans, not with life, not even with the planet itself. It begins in emptiness, in the raw material that preceded everything, in the debris field of ancient suns, in forces so immense and so patient that no human mind can fully absorb them, no matter how long you sit with the numbers. This is not a story about discovery. It is not a story about exploration. It is not a story of kings or empires or revolutions. This is the story of how the world beneath your feet was forged, through violence so total, so unrelenting, so almost incomprehensible in its scale, that the word catastrophe barely begins to cover it. And it is, in the most fundamental sense possible, the story of everything that comes after. Because before there could be life, there had to be Earth. Before there could be Earth, there had to be a sun. Before there could be a sun, there had to be the death of something that came before. The universe does not build from nothing. It builds from wreckage. That is where we begin. In the wreckage. To understand how Earth was born, you first have to understand where it came from. And that means going back much further than 4.6 billion years. It means going back to the stars that died long before our own star ignited. The universe is approximately 13.8 billion years old. For the first several hundred million years of its existence, it contained only the simplest elements. Hydrogen and helium, with trace amounts of lithium. There was no carbon, no oxygen, no iron, no silicon. None of the heavier elements that form the building blocks of rock, of metal, of water, of biological molecules. None of the ingredients that would eventually produce you. Those heavier elements had to be made. They were made inside stars. Stars are nuclear furnaces. At their cores, under pressures and temperatures that dwarf anything achievable on Earth's surface, hydrogen atoms are crushed together into helium, releasing enormous amounts of energy in the process, the energy that makes a star shine. But as a star ages, it progressively fuses heavier and heavier elements. Helium becomes carbon. Carbon becomes oxygen. Oxygen becomes neon, magnesium, silicon. The chain of fusion continues, building the periodic table one element at a time, locked away inside stellar cores. And then the star dies. When a sufficiently massive star reaches the end of its life, it explodes in an event of almost incomprehensible energy, a supernova. In the space of seconds, a supernova releases more energy than our sun will emit across its entire 10 billion year lifespan. The explosion tears the star apart, blasting its contents. All those heavy elements built up over millions of years of nuclear burning, outward into space at a significant fraction of the speed of light. Those elements drift through the galaxy. For millions, sometimes billions of years, they travel as diffuse clouds of gas and dust, the scattered legacies of stars that no longer exist, until eventually they encounter other clouds, mix with them, and become part of the raw material of the next generation of stars and planets. Every planet in our solar system, including Earth, is built from this inherited material. The iron in Earth's core was forged in a dying star. The oxygen in the atmosphere was synthesized in a stellar interior. The carbon in every living cell on the surface of this planet was produced in a nuclear furnace that burned out billions of years before life existed. We are all of us, the children of dead stars. The universe recycled itself to build us. Approximately 4.6 billion years ago, in one spiral arm of the Milky Way galaxy, a particular cloud of this stellar debris reached a critical point. Scientists call it the solar nebula, a vast, slowly rotating mass of gas and dust, mostly hydrogen and helium by volume, but laced throughout with the heavier elements inherited from previous generations of stars. The cloud was enormous. If you could somehow spread it flat, it would have covered a region hundreds of times larger than our current solar system. It had been drifting, slowly rotating, for an incalculable period of time, until something disturbed it. What triggered the collapse is still a matter of active scientific discussion. The most widely cited hypothesis is that a nearby star reached the end of its life and exploded in a supernova, sending a shockwave rippling outward through space that compressed the edge of our nebula, disturbing the delicate equilibrium between the outward pressure of the gas and the inward pull of gravity. Once that equilibrium was broken, gravity won. And gravity, given enough time and enough mass, is unstoppable. The cloud began to contract. As it did, something predictable but remarkable happened. It began to spin faster. This is the same principle that causes a figure skater to accelerate when they pull their arms inward. The conservation of angular momentum. The nebula had always been rotating slightly, but as it shrank, that rotation accelerated dramatically. Slowly at first, then faster. A vast, diffuse cloud became a tighter, faster spinning disk. At the center of this collapsing disk, material was accumulating at an extraordinary rate. The temperature began to rise. The pressure began to build. Over roughly 100,000 years, a blink of cosmic time, the core of the collapsing cloud reached approximately 10 million degrees Celsius. At that temperature, a threshold was crossed. Hydrogen nuclei began to fuse into helium. Nuclear fusion ignited. The sun switched on. For the first time in the history of this region of the galaxy, there was light here. A star, our star, blazed to life at the center of a swirling disk of leftover gas and dust. That disk was the raw material of everything that followed. Around the newborn sun, the remaining material from the nebula had not disappeared. The collapse that ignited the sun had swept most of the mass into the center, but a significant fraction remained in orbit, flattened by centrifugal force into a broad, flat disk that extended outward from the sun for hundreds of millions of kilometers in every direction. This was the protoplanetary disk. And within it, the process of planet building had already begun. It started small, extraordinarily, almost insultingly small. Individual grains of dust, silicate particles, carbon compounds, ices, collided gently with one another and stuck together. These collisions happened countless times per second, across a disk billions of kilometers wide. The grains became clumps. The clumps became pebbles. The pebbles became cobblestones. The cobblestones became boulders. The boulders, over hundreds of thousands of years of continued accumulation, became bodies the size of mountains, then the size of cities, then the size of small moons. Scientists call these objects planetesimals. They were the building blocks of the planets. Irregular, tumbling, rocky and icy bodies that ranged in size from a few kilometers to hundreds of kilometers across. The protoplanetary disk was filled with them. Billions upon billions of planetesimals, each one carving its own path around the sun, each one growing with every collision, each one drawing in more material through the sheer force of its own increasing gravity. But here is the thing that textbooks often fail to convey. This was not a quiet, orderly process. It was not slow and serene, like watching sediment settle at the bottom of a lake. It was catastrophic. Think about what it actually means for two bodies, each the size of a mountain range, each composed of rock and metal and ice, to collide at tens of thousands of kilometers per hour. The impact releases energy that makes nuclear weapons look like firecrackers. The collision either shatters both bodies completely, sending debris flying in all directions, or it partially merges them into a new, larger body, itself irregular and damaged, its surface scarred and molten from the energy of impact. And in the early solar system, these collisions happen constantly. Not once a century, not once a millennium. Constantly. The inner solar system was, for tens of millions of years, one of the most violent environments that has ever existed. A cosmic demolition derby where the debris field was itself the construction material, where destruction and creation were the same process happening simultaneously. Most planetesimals never survived long enough to become planets. They were shattered and absorbed, their material redistributed into larger bodies, their individual existence erased. But some survived. Some grew large enough that their gravitational influence began to dominate the region of space around them, sweeping up the remaining material in their orbital path. growing larger with every encounter, every merger, every captured fragment. These survivors, scientists call them planetary embryos, were the protoplanets, bodies comparable in mass to the Moon or to Mars, each one carrying within itself the seeds of what would eventually become a full-sized planet. One of these embryos was on a trajectory that would lead, through billions of years of further violence and transformation, to the world we call Earth. For tens of millions of years, the inner solar system was a battlefield on a scale that strains the imagination. Planetary embryos, dozens of them, each the size of Mars or larger, crossed each other's orbital paths. Gravitational resonances between the giant planets forming in the outer solar system sent shockwaves through the inner disk, destabilizing orbits, redirecting embryos onto collision courses. Giant impacts, involving bodies hundreds of kilometers across, were not rare accidents. They were the dominant process. Through this violent winnowing, four terrestrial planets emerged: Mercury, Venus, Earth, and Mars. Each one is the survivor of a process that destroyed far more than it created. For every planet that made it to the modern solar system, countless planetary embryos were shattered, absorbed, or flung out of the inner solar system entirely. Our proto-Earth, at this stage, was not recognizable as a planet. It was a misshapen, irregular body of enormous size, already massive enough to retain a gravitational field far stronger than anything on its surface, but continuously being reshaped by the relentless bombardment it was enduring. Its surface was not solid. It could not be solid. The energy delivered by the constant impacts, each one releasing enough heat to melt rock, kept the surface in a perpetual state of liquid fire. Scientists call this the magma ocean phase, and it represents one of the most extreme environments that Earth has ever experienced. For much of the first 100 million years of its existence, our planet's surface was a global ocean of molten rock, hundreds of kilometers deep, churning and convecting, lit from within by the decay of radioactive elements that had been incorporated into the planet's body during its formation. Beneath that molten surface, something critically important was happening. As the proto-Earth grew and the temperature at its center rose, the planet began to sort itself out. The heavier elements, primarily iron and nickel, being denser than the surrounding rock, began to sink toward the center. The lighter silicate materials, the stuff of granite and basalt and sand, migrated upward. Over millions of years, through a process geologists call planetary differentiation, the initially homogeneous body of rock and metal separated into distinct layers. A dense iron-nickel core at the center, a thick rocky mantle surrounding it, and the beginnings of a thin outer crust at the surface. This differentiation was not just a structural reorganization. It had profound long-term consequences that reach all the way to the present day. The iron core, as it cooled, and as the inner portion solidified while the outer portion remained liquid, became a dynamo. The convection of liquid iron within the outer core generated electrical currents, and those electrical currents generated a magnetic field. A global, planet-wide magnetic field that extended far into space above the surface. That magnetic field is Earth's invisible armor. Without it, the solar wind, the constant stream of charged particles blowing outward from the sun at hundreds of kilometers per second, would strip away the planet's atmosphere over geological timescales. Mars, which lost its magnetic field billions of years ago, still bears the consequences. Its atmosphere was gradually eroded, its surface water evaporated into space, its climate collapsed. Mars today is a frozen desert, the ghost of a world that might once have been habitable. Earth kept its magnetic field, and because it kept its magnetic field, it kept its atmosphere. And because it kept its atmosphere, it was eventually able to support life. The iron sinking to the center of the proto-Earth was, in a very real sense, one of the earliest prerequisites for our existence. Around 4.5 billion years ago, approximately 50 to 100 million years after the sun ignited, the young Earth endured the single most catastrophic event in its history, an event so violent, so total in its destruction, that it reshaped the planet from top to bottom. And yet, paradoxically, improbably, it may have been one of the best things that ever happened to life on Earth. The event is known as the Giant Impact. The body responsible has been named Theia, after the Titan goddess who in Greek mythology was the mother of the moon. And the name is fitting, because what Theia left behind, after its collision with Proto-Earth, was the moon itself. The details of the Theia impact are still actively debated among planetary scientists. But the broad outlines of the giant impact hypothesis, first proposed in the 1970s and now supported by a substantial body of evidence, are widely accepted. Theia was a body roughly the size of Mars, perhaps a third of Earth's current mass. It had formed in the same region of the protoplanetary disk as Earth, and for millions of years had coexisted with Proto-Earth in nearby orbital paths, held in a gravitational relationship that planetary scientists call a Trojan configuration. But that configuration was not stable forever. Gravitational perturbations from the giant planets, Jupiter most likely, slowly destabilized Theia's orbit over millions of years. Its path began to drift, and eventually, inexorably, its trajectory intersected with Earth's. The collision that followed was not a head-on impact. The current models suggest it was a glancing blow, a grazing strike at a relatively shallow angle, which had enormous consequences for what happened next. The force of the impact was staggering. The kinetic energy released in those first moments was equivalent to billions of the most powerful nuclear weapons ever conceived, all detonating simultaneously. Theia did not leave a crater. The impact was so energetic that both bodies were partially vaporized. The outer layers of Proto-Earth and the outer layers of Theia were blasted outward into space in an expanding plume of superheated rock vapor and molten debris. The deep interiors, the iron cores of both bodies, merged, combining into a single, larger mass that would become the core of the modern Earth. The two planets, in a very literal sense, became one. But the debris that was ejected into orbit did not simply drift away into space. Gravity pulled it back. The cloud of vaporized rock and molten droplets that now surrounded Earth was dense enough, and close enough, that within a geologically astonishing time frame, perhaps just a few decades to a few centuries, it coalesced into a new body. A satellite. The moon. Our moon is, in a very real sense, a piece of Earth. The isotopic signatures of lunar rocks returned by the Apollo missions are nearly identical to those of Earth's mantle, evidence that the two bodies share a common origin, that the moon was built largely from Earth material blasted into orbit by the Theia impact. The consequences of this event echo across all of subsequent Earth history. The impact tilted Earth's rotational axis to approximately 23.5 degrees relative to its orbital plane. That tilt, maintained and stabilized over billions of years by the gravitational influence of the moon, is responsible for Earth's seasons. Without the tilt, there would be no summer, no winter, no annual cycle of temperature and light that drives so much of the biology we see today. The impact also dramatically accelerated Earth's rotation. In the immediate aftermath of the Theia collision, a day on Earth lasted only about 6 hours. The planet was spinning nearly 4 times faster than it does now. Over billions of years, the moon's tidal forces have gradually braked that rotation, transferring angular momentum from Earth's spin to the moon's orbital energy, a process that is still ongoing. The moon is still slowly moving away from Earth, at approximately 3.8 centimeters per year. The day is still, imperceptibly getting longer. And perhaps most critically, the moon stabilizes Earth's axial tilt. Without the moon's gravitational steadying influence, the tilt of Earth's axis would be chaotic, varying wildly over millions of years, potentially swinging from near zero to extreme angles. Such instability would cause catastrophic climate swings. Ice ages would be more severe. Equatorial regions would periodically freeze. Temperate zones would become uninhabitable. The stable, relatively predictable climate that allowed complex life to evolve and diversify over hundreds of millions of years might never have developed. We exist in part because Theia died. The planet that struck us gave us our moon. The moon gave us our seasons, slowed our days, and held our axis steady. And the steady axis held our climate in a range narrow enough for life to flourish. Catastrophe, as it turns out, can be the greatest act of creation. After the Theia impact, Earth entered a phase known as the Hadean Aeon, a name drawn from Hades, the Greek underworld. Few names in all of geology are as apt. The Hadean Earth was, by any measure imaginable, a hell world. The impact had remelted the surface entirely. Whatever fragile crust may have been forming before the collision was obliterated. The planet was once again a global magma ocean. Perhaps even more extreme than before, because the energy of the Theia impact had been added to all the heat already present from the accretion process and from radioactive decay. The surface temperature was likely several thousand degrees Celsius. The atmosphere, if you could call it that, was a thick, crushing blanket of steam, carbon dioxide, methane, sulfur dioxide, and other volcanic gases. There was no liquid water, no solid ground, no sky in any meaningful sense of the word. Just a hellish, churning expanse of liquid rock beneath a poisonous, superheated atmosphere. And the moon, newly formed and enormously close, perhaps 10 times closer than it is today, loomed enormous in the sky above this burning world. Its gravitational pull raised tides in the magma ocean hundreds of meters high. The young Earth groaned under those tidal stresses, which generated additional heat, keeping the surface molten for longer than it would otherwise have remained. The bombardment from space had not stopped, either. The early solar system still contained vast quantities of leftover material, asteroids, comets, and planetesimals that had not been incorporated into the planets during the accretion phase. These objects continued to rain down on the inner solar system for hundreds of millions of years after the planets formed. Some of these impactors were enormous, large enough to partially remelt portions of the surface on impact, large enough to blast debris back into space, large enough to leave scars the size of continents. Scientists believe that approximately 4 billion years ago, the rate of impacts spiked dramatically in an event known as the Late Heavy Bombardment. The cause is still debated, but the most widely accepted explanation involves the migration of the giant outer planets, Jupiter and Saturn, shifting their orbits in ways that destabilized the asteroid belt and sent a cascade of rocky bodies raining inward through the solar system. The scars of this bombardment are preserved on the Moon's surface. The large impact basins visible to the naked eye on a clear night are mostly relics of this period. On Earth, the geological record of the Late Heavy Bombardment has been largely erased by billions of years of plate tectonics and erosion, but it almost certainly occurred here as well. The Hadean Earth endured all of this. And yet, and this is the part that continues to astonish scientists, the Hadean was not entirely without the first tentative hints of what was coming. In 2001, a team of geologists working in the Jack Hills region of Western Australia announced a discovery that sent shockwaves through the earth sciences community. They had found tiny crystals of a mineral called zircon, among the most chemically durable minerals that exist, with radiometric ages of 4 billion years. Those crystals are the oldest solid material ever found on Earth's surface. But the crystals themselves were not the discovery. What made the Jack Hills zircons so extraordinary was their chemistry. The oxygen isotope ratios preserved within those ancient crystals were inconsistent with formation in a completely dry, magma-dominated environment. They were, instead, consistent with formation in the presence of liquid water, possibly even in the presence of relatively cool, wet conditions at the surface. If that interpretation is correct, and it remains controversial, it means that liquid water was present on Earth's surface as early as 4.4 billion years ago, even during the height of the Hadean bombardment, even when, by all appearances, the planet should have been far too hot and far too violent to sustain anything resembling surface water. Where did that water come from? The answer is almost certainly from space. Comets are largely composed of water ice. Certain classes of asteroids, the carbonaceous chondrites, also contain significant quantities of water locked within their mineral structure. As these objects rained down on the Hadean Earth during the bombardment, they delivered their water cargo directly to the surface. The very impactors that were bombarding the planet were also, simultaneously, hydrating it. The same process that was making Earth's surface so hostile was also delivering the single most essential ingredient for life. The building blocks of life's one absolute requirement, water, were arriving even in the midst of the violence. By approximately 4 billion years ago, the most extreme phase of Earth's early history was drawing to a close. The pace of impacts was slowing. The solar system had cleared most of its leftover debris. The surviving planets had settled into stable orbits. The late heavy bombardment, whatever its precise cause, was winding down. The interior of the Earth had largely completed its differentiation. The core was established, the mantle was structured, and the crust, though still thin and fragile, was beginning to persist in coherent form. And then something happened that changed the planet forever. The oceans appeared. It did not happen overnight, and it did not happen all at once. Over a period of perhaps several 100 million years, as the surface cooled and the atmosphere lost some of its crushing water vapor content, liquid water began to accumulate on the surface. First in shallow puddles in topographic low points, then in ponds, then in lakes, then in increasingly vast expanses that would eventually cover most of the planet's surface. The question of where Earth's water ultimately came from is one of the most actively debated problems in planetary science. Was it delivered primarily by comets, as the early bombardment models suggest? Was it carried in by water-rich asteroids from the outer regions of the asteroid belt? Was much of it outgassed from Earth's own interior through volcanic activity, as water molecules trapped in magma were released during eruptions? Most researchers today suspect the answer involves contributions from all three sources, in proportions that are still being worked out. But the mechanism is, in some ways, less important than the result. The result was an ocean that was, by the standards of everything that had come before, quiet. The surface was still volcanic, enormously so, by any comparison to the modern Earth, with volcanic activity at a scale that would dwarf the largest eruptions of recorded human history. The atmosphere was still toxic, rich in carbon dioxide, nitrogen, methane, and other compounds, with essentially no free oxygen. The sky would have been hazy, perhaps orange or pale yellow, filtering the light of a sun that was actually somewhat dimmer than it is today. The moon was still much closer than it is now, raising tides of extraordinary height across the shallow coastal basins. But there was liquid water, standing, pooling, collecting in vast quantities on the surface of the planet. And in that water, chemistry was beginning, slowly, blindly, patiently. The complex molecules of carbon, hydrogen, oxygen, and nitrogen that had arrived with the comets and asteroids were dissolving, mixing, reacting. Volcanic vents on the ocean floor, superheated chimneys of chemical energy, were releasing hydrogen sulfide, methane, and mineral-rich fluids into the surrounding water, creating gradients of temperature and chemistry that could drive reactions impossible in calmer environments. The stage was being set, not for civilization, not for intelligence, not for anything that would be recognizable to a human observer for billions of years to come, but for something. It is genuinely difficult to hold the timescales of this story in your mind, not because the numbers are too large to say, they are not, but because they are too large to feel. We say 4.6 billion years, and the words are simple enough. But the reality behind those words is almost entirely resistant to human intuition. Consider the entire span of recorded human history, from the invention of writing to the present day, covers approximately 5,000 years. The rise and fall of the Roman Empire, one of the most consequential political entities in Western history, occupies roughly 1,000 years. The full sweep of human civilization, from the earliest cities of Mesopotamia to the modern world, is perhaps 7,000 years. Set that against the 700 million years of the Hadean Aeon, or the 50 million years it took for the protoplanetary disk to coalesce into recognizable planets, or the 100,000 years it took for the solar nebula to collapse into a star. The formation of Earth did not happen quickly by any standard except the cosmic one. And even by cosmic standards, Earth is not old. The universe is 13.8 billion years old. The Milky Way galaxy formed perhaps 13.6 billion years ago. The first stars ignited within a few 100 million years of the Big Bang. By the time our solar system formed, 4.6 billion years ago, the universe was already more than 2/3 of the way through its current age. We are newcomers. This planet is a newcomer. We arrived late to a universe that had already been running for 9 billion years. And yet we are built from that universe's history, built from the wreckage of stars that burned and died before our sun existed. The carbon in every molecule of DNA in every cell of your body was synthesized in a stellar interior that no longer exists. The iron in your blood was forged in a supernova shockwave. The calcium in your bones was scattered through space by a dying star. The oxygen you breathe was manufactured in nuclear furnaces spread across billions of years and billions of light-years of cosmic history. When Carl Sagan said that we are made of star stuff, he was not speaking metaphorically. He was stating a chemical fact. Every atom heavier than helium in the known universe was created inside a star. And every one of those atoms has been on a journey, through stellar interiors, through supernova explosions, through interstellar space, through the collapse of a nebula, through the violence of planetary formation, before ending up here, now, assembled into the improbable complexity of a living human being reading or listening to these words. The violence that built this world was not random destruction. It was construction by another name. Every collision between planetesimals added mass. Every impact delivered heat that drove differentiation, building the core and the magnetic field. The Theia impact gave us our moon, our tilted axis, our seasons, and our stable climate. The late heavy bombardment delivered water and carbon compounds. Every eruption in the Hadean added gases to the atmosphere and minerals to the forming ocean. All of it was, in retrospect, preparation. The universe was, without intention or purpose or awareness of any kind, assembling the conditions for something it had never produced before. A rocky planet, at just the right distance from its star, with liquid water on its surface, with a magnetic field to protect that surface, with a large moon to stabilize its axis, with a rich chemistry in its young ocean. A planet, in other words, that was ready. Ready for what? That is the question that drives the next chapter of this story. The oceans have formed. The crust has solidified. The bombardment has slowed to a pace that the planet can absorb without being remelted. But the story of Earth is far from over. In fact, in the most important sense, it has barely begun. Because now, in the depths of those first oceans, something is happening. Something that, even now with all the tools of modern science, we do not fully understand. Something that, when it finally occurs, will transform this planet from a lifeless ball of rock and water into something that has never before existed in the known history of the universe. Life is coming. Not yet. Not for hundreds of millions of years yet. The ocean is still dark and acidic and chemical. The atmosphere is still toxic. The sun's ultraviolet radiation still penetrates to the surface without the protection of an ozone layer, because there is no ozone. There is no free oxygen to make ozone from, not yet. But the chemistry is running. The molecules are reacting. The volcanic vents on the ocean floor are pouring energy into the system, hour after hour, year after year, millennium after millennium. Somewhere in those early oceans, in conditions that we are still working to reconstruct, the first steps toward the first living thing are being taken. Before we get there, however, there is still more of Earth's early story to tell. The crust is thin and fragile, but it will not always be. Plate tectonics, the great engine of geological change, is stirring. Continents will eventually form, drift, collide, and break apart. The atmosphere will transform, dramatically more than once. The chemistry of the ocean will shift. The climate will swing between extremes we can barely conceive of today. And in the next episode, we go deeper into the story of Earth's first great environmental transformation. The formation of the first stable ocean, and the deep question of what was stirring in its waters. Because out of this world of fire and poison and darkness and chaos, something unimaginable was quietly assembling itself in the deep. That story, the story of Earth's first ocean, and what it meant for everything that came next, is where we go next. There is one more thing worth saying before we leave the Hadean behind. When geologists and planetary scientists study this period, they do so almost entirely without direct evidence from Earth itself. The reason is simple. The Hadean Earth was so geologically active, so constantly being reshaped by impacts and volcanism, and the movement of a crust that was still finding its form, that virtually no surface rock from this period has survived. The oldest intact rock formations on Earth, found in Canada's Northwest Territories, in formations known as the Acastinices, are approximately 4.03 billion years old. They date not from the Hadean, but from the very beginning of the subsequent Eon, the Archean. The Hadean itself, for Earth, is almost entirely a blank. We know it happened because physics and chemistry and planetary science tell us it had to. We know its broad outlines because we can reconstruct them from the evidence that does survive. Those ancient Jack Hill's zircon crystals, the chemical fingerprints left in the oldest rocks, the preserved record of impacts on the moon's surface, and the comparative study of other planets and moons that have not been as thoroughly erased by time and geology as Earth has. But the direct testimony of the Hadean Earth is almost entirely lost, which means that this period of Earth's history, arguably the most dramatic, the most violent, the most consequential in terms of setting up everything that followed, is also the most mysterious. We are reconstructing it from fragments and inference, from chemistry and physics, from the traces left behind in minerals durable enough to survive for a billion years of geological processing. There is something deeply appropriate about that. The most fundamental chapter of Earth's story is also the hardest to read. The world that was built in fire and impact and bombardment left almost no written record of itself. We know it happened. We know it mattered. But much of exactly how it unfolded, which impacts happened in what order, how long the magma ocean lasted, when exactly the first stable crust appeared, when exactly liquid water first pooled on the surface, remains genuinely, fascinatingly uncertain. Science is still reading the opening pages of Earth's story. And every new zircon crystal, every new isotopic analysis, every new comparative study of other planetary bodies in our solar system adds a few more words to our understanding of a chapter that was written in rock and fire 4.5 billion years ago. We are, in a sense, archaeologists of the solar system's own violent birth, and what we are uncovering, piece by careful piece, is the story of how the most improbable place in the known universe came to exist. This planet, this world. The only one, as far as we know, where the chemistry went all the way. The next chapter of that story begins in the darkness of the first ocean, and it is stranger than anything we have encountered so far.